Okay, hello everyone, welcome back to our episode 11 of the number series. For today's video, we'll be talking about quadratic congruences and the problem at the end of the book. So the first problem, we will be solving those basic quadratic congruence. Well, first, we just need to determine if it has solution or not. And how we do this is use the Legendre symbols and using the three laws over here, three different laws, and also the quadratic reciprocity theorem here. And we can just quickly get if it has a solution or not. If the function returns a value of 1, it means it has a solution. Otherwise, if it's -1, well, it means there's no solutions. And there's really nothing much to tell about how do you find the solution, and you are just basically going to try every single one of them and until you find a square, and that's it. And like this is an exception. If this is a square, you can immediately know what is the value, because x equals, like this one, 25. You know the square root of 25 is 5, and you can get a result instantly. And more practices. Okay, we need to find more solutions. Well, just check your work, alright? It's not too difficult. And 5 and 6, we're gonna calculate a bunch of values. Well, it's just calculating, so this is just the answer. I also made a program and just calculating it using those three laws and the quadratic reciprocity, and also theorem number 6 about 2/p. And yeah, that's how we calculate it. I just plug in into the computer. I am too lazy to do this by myself. So, okay. Question 7. We need to solve those two equations. Well, if you see some very simple quadratic equation like this, and it's factorable, and you can just factor this and try to make each factor a multiple of the modulus. For example, this one, after you factor this, you plug in x equals to 50 and x equals to 100, and you're gonna get a result instantly. Well, you can also just do what does the book wants you to. And first, you're gonna make the ax squared, you make the a equals to 1. We know that for a given coefficient, after you multiply some numbers between 1 to 7, it's going to change it to 1. For example, 2 multiply 4 and take the remainder of 7 is equals to 1. And then you're gonna check the value of b. If this is odd, you're gonna simply plus the modulus x and make it even numbers, and you're gonna make a square, and the rest of the number you put it on the right side, and you solve the Legendre symbol. And to find the solution, you just brute force it. Okay. And question 8, just 2 more examples, and those two are actually the same, and I didn't notice it for the first time, but after I see the result, well, after you just take the remainder of 52, you're gonna find those two are exactly the same. Okay, question 9, we're gonna calculate those very, very long Legendre symbols. Well, the technique still holds, and I'm gonna give you one example how to solve it in general. First, you're gonna write it. You're gonna factor out 1234, which is here, into different prime numbers, and if it hits 2 over here, you're gonna check the modulus 8 of these numbers, and according to theorem 6, if it's congruent to 1 or 7, then it's equal to 1. Otherwise, if this is congruent to 3 to 5, then it does not have a solution. It returns -1. So this one, and we use the quadratic reciprocity, and we factor out this number. And if you factor out a square, you can just make it 1, okay? Like why I just did this. This is a multiple of 8, and you're gonna factor out a 4. And 4 is a square, and you make it 1, and we don't care, and we have one single 2 left here. And yeah, just theorem 6 again, and quadratic reciprocity here. And then we gonna factor out the 4 here, and we use the quadratic reciprocity again, okay? And we get this, and this is a square, and it equals to 1. Very simple, right? And 4 more questions, that's the answer. And question 11, show that if P equals to Q plus 4A, PQ are odd primes, then the Legendre symbol of P/Q is equals to A/Q. So we know that P/Q, we rewrite P using Q and A, and we take the remainder of this, and we factor out the number 4 here, and we have only A left. This is equal to 1, okay? And question 12, show that P equals to 12K plus 1. For some K, then 3/P equals to 1. Okay, so we know this is a form of 4K plus 1, and this is 3. So the quadratic reciprocity is just going to be the same. And we're gonna take the remainder of 3, and we have 1/3, and this is equals to 1. Question 13, show that theorem 6 could also be written as 2/P equals to -1 to the power of P squared minus 1 divided by 8. Well, we can make a small table, and this is going to be the result of this whole thing, and it is exactly the same like the theorem 6 over here. Okay, question 14, show that the quadratic reciprocity theorem could be written as P/Q or times Q/P equals to -1 to the power of P minus 1 times Q minus 1 divided by 4 for odd prime P and Q. Well, if they are either one of them equals to 1, this thing is going to be equals to 1. Otherwise, if they are both 3, it's going to be -1, okay? And question 15, student A says that I have checked all the way up to 100 and I still couldn't find a value of n so that n squared plus 1 is divisible by 7. I'm tired now, I will find one tomorrow. Student B thinks for a few seconds and says you won't. How did B know so quickly? So this is what he is trying to find. And we know that 6 is not a quadratic residual. According to the Legendre symbol here, we factor out, we use theorem 6, we quadratic reciprocity again, and this is equal to -1, and he will never find a number for which n squared plus 1 is divisible by 7. It's impossible. And question 16 shows that if A is a quadratic residual modulus P and A times B congruent to 1 modulus P, and then B is a quadratic residual modulo P. So we know that A times B, the remainder is equal to 1, and we can solve it and find that this is equal to 1. And 1 equals to this thing, and we can factor this out to A/P times B/P. And we know this is 1 given in the question, and this thing left, the product of this equals to 1, and this has to be 1. And we know then B is a quadratic residual. Question 17. Does this thing have a solution? And note that 159 is not a prime. And we're gonna split this up into 2 different congruences, and we get general solution here. And we need to make sure that the solution satisfy one of this and one of this. And we can give an example that x equals to 136 is indeed a solution. Question 18. So prove that if P is congruent to 3, modulo P and P minus 1/2 is prime, then P minus 1 over 2 is the quadratic residual. So we know that P is congruent to 3 and it can be expressed in form like this. When we divide it by 2, it's 4k plus 1. And that means the quadratic reciprocity is just going to be the same as the original number. And we take the remainder and we have 1 left. And this thing is equal to 1. And question 19. Generalizing the problem 16 by finding what condition on R will guarantee that if A is a quadratic residual modulo P and AB congruent to R modulo P, then B is a quadratic residual of P. Okay, so we know that as long as this thing here is equal to 1, and we can use this technique here. And this thing is going to be equal to 1 as long as AB is a quadratic residual. In other words, R is equals to a quadratic residual. That's it. And question 20. Suppose P equals to Q plus 4A, where PQ are odd primes. Show that A over P equals to A over Q. So they have the same remainder of 4, and then we know that they both either have -1 or they both don't have it. So we can just have this equality over here and we flip it around, and then we take the remainder of this one and we're gonna find Q over A and Q over A, and this is equal. Alright, that concludes our section for today. I know it's a little short today because there's a lot of calculation problems and it's kind of boring. So that's why this video is probably the shortest one so far. But anyways, I still hope you guys enjoy the video and see you in the next one. Bye bye.